We'll begin again with our demotivational poster. Consistency. Occasional excellence is rewarded by higher expectations, while sustained mediocrity is rewarded by promotion. If you like these things, you might want to read Scott Adams' Dilbert. They're pretty funny sometimes. I had an engineer friend who worked at Hewlett-Packard, and he said that he would read Dilbert. He and his friends, his engineer friends, would read Dilbert, and it seemed like they worked at Hewlett-Packard alongside him and were finding material there. So it's a common theme, common things in industry that engineers deal with, and I'm sure that engineers cause problems with too. So the topic today is rolling contact bearings, and rolling contact bearings are a little different than plain bearings, but we'll get into plain bearings later. There are several major manufacturers of Timken. Here are just 5. There are others. Timken, SKF, FAG, NTN, and SK. A lot of these seem to have 3-letter abbreviations, and I don't really know what most of them stand for, but very common companies. You'll see these bearings everywhere. But some bearing terminology. The bearing itself consists of several common components. Some bearings have all of these, some have fewer. They all have rolling elements. That's the key feature we're studying in this chapter. So there's the outer race, the inner race. The cage kind of holds the rolling elements in place, not so that they can't move, but just to keep them from moving all to one side, which is typically how you assemble these bearings. And of course the rolling elements themselves, the pins to hold the cage together if necessary, and so forth. What we're more interested in are things like the bore, which is the hole through the center and its size, the width of the bearing, and the outside diameter of the bearing, and of course the particular rolling elements. There are many different options in that arena for the rolling elements themselves. If we expand the bearing so you can see it, this is just a simple ball bearing, and it's one of the simplest. You can see the inner and outer races as well as the rolling elements, the balls themselves, in the cage. There are several different types of bearings, and we'll go through them. Now, we're going to see them all in cross-section. I've brought some example bearings, and I hope the camera can pick this up okay, but this looks just like the picture we saw a moment ago. And you can see the balls, hopefully, behind the cage. You can see how the inner race, of course, can rotate easily, and the bearings just move along with it. This particular one, made in USA, Fafnir, F-A-F-N-I-R is the name of this company, and I'm not sure if they're still in business or not. I'm not sure how many bearings are actually made in the United States anymore. Apparently bearings have gone. They used to be made in both metric and English sizes, and today the only thing that's really commonly available are metric sizes. That's one place where metric has really taken over. Oh, but if you imagine, the picture you're seeing on the screen is basically just this bearing cut up here. So I'm not showing the whole thing. So you can imagine an axis horizontal on the screen that represents an axis of revolution, right, where you would revolve this cross section 360 degrees around that axis and end up with this type of bearing. So that's one type of bearing, just a plain ball bearing. It's a single row of balls, and it can take significant radial loads. Now, when I say radial loads, what I mean is that the load is radial acting to the bearing. Okay, so it's perpendicular to the shaft, and it can take light thrust loads. So if the shaft is in the bearing, the thrust load would be applied between the inner and outer races, and this type of bearing can only take light thrust loads. There are also double row ball bearings like this, where you basically have just 2 rows side by side. These can take heavy radial loads and still only light thrust loads. And the reason these things can only take light thrust loads is because the groove, the raceway groove in the inner and outer bearing are not all that deep. There are also self-aligning double row ball bearings, and I meant to bring one of these and forgot to grab it, but these are a pretty simple idea. It's kind of like the double row ball bearing, except that instead of the outer raceway having 2 grooves for each set of balls to ride in, rather it's more of a spherical shape. It's part of a sphere. And the idea here is that the inner race can rotate relative to the outer race, and this allows for misalignment between the inner and outer race, or the shaft and the frame, essentially. Now, just like the double row ball bearing, these things can take heavy radial loads, but only very light thrust loads. And the reason for that is that spherical shape is not deep at all, and so it's pretty easy, relatively easy, to damage the bearing with a significant thrust load. But the advantage of these is they can take fairly high angles of misalignment between the inner and outer race. And so you see the spec here of about 4 degrees of misalignment. It depends on the particular bearing, the manufacturer, and so forth, but that's a decent estimate. There are also what's called angular contact bearings. Now these are ball bearings that are very much like just a single row. The difference is that rather than just having a symmetrical groove to ride in, these have a groove that is offset. So you can see that there's a little more material on the top left and the bottom right, and what this does is allow a significant thrust load. Now only in one direction, right? You can't take an angular contact bearing and thrust in both directions between the inner and outer race. You can only thrust in one particular direction, so you have to install it in the right orientation, and it can only take thrust loads in one direction, so you have to know which direction that is. It's pretty easy to see by looking at the bearing typically, especially if you're used to looking at it and you know what you're looking for. But these can take much heavier thrust loads, so they take a combination of radial and thrust loads. Now there are also cylindrical roller bearings. Now we're moving from balls, things that are round and that contact theoretically at a single point, to elements that contact at a line. Now these are just simple cylinders. I hope you can see it. This particular one, I don't have the inner race to it. I only have the outer race, the cage, and the rolling elements. And you can see the reason why these can't take any thrust loads. Probably that's the reason that I lost the inner race, right? It simply slips out. There's nothing to prevent it from coming out in one direction. Now typically, and now this apparently, I don't know how they've done it, but they've somehow captured the rolling elements themselves in the outer housing. Probably it's some type of engagement between the cage and the outer race. Anyway, you can see how in the schematic here of half of the bearing that the outer race and the inner race wrap around the elements just a little bit. Well, those are, if you think about what's going on there, there's going to be significant sliding between the rolling elements and the rolling element, and you don't want that to happen. You don't want those to slide relative to another because they'll wear fairly quickly. So no thrust loads are allowed, but very heavy radial loads can be supported by this type of bearing, and they're also good for high-speed operation. There are also what are called needle bearings. Needle bearings are interesting. This is kind of a different needle bearing. It's different than the usual ones that you see. I'll take the fastener out that's in the middle of it, and you might say, well, why wouldn't you design the you might notice there's an inner race here. You might say, why wouldn't you design this to run directly on this shaft? Well, some actually are. The problem is, as we're going to talk about later, the inner and outer raceways have to be made very hard, because it turns out that there's going to be fatigue of the materials, which you're really concerned about. And every time a rolling element comes around, it doesn't really matter if it's a ball or a cylindrical element. The contact is theoretically either a point or a line, and so the amount of stress is theoretically infinite. In other words, the balls have to flatten out a little bit, the rolling elements flatten out a little bit, and then the raceways will flatten out a bit as well. Not much, but it is a significant amount. It does happen. And so if you think about what's happening on the raceways, they're being fatigued, right? They're being loaded and unloaded repeatedly with compressive stress and then zero stress. If you do that to the surface of this bolt, it won't last very long at all. You have to have hardened material to have significant fatigue life and resist that loading. Now this is interesting because I can actually disassemble the entire needle bearing set, and you notice that they're held, you can't feel it, but they're held fairly loosely. I can move them up and down. There's a lot of play against the cage. But they're designed to be run either directly on a hardened shaft, or in this case on an inside raceway and an outer raceway. Now the inner and outer raceways have to be hard. You can't just run a needle bearing on any old shaft. It won't work. The shaft has to be made very hard in the section where the needles are going to run, otherwise it'll wear out very quickly. And the most common setup is an outer cage with the needle rollers in it that then ride on a shaft that's been appropriately hardened. Now you might look at this and say, well, how is this different from a cylindrical element? Well, it's not really, right, because these are still cylindrical elements, but they're typically very long, very thin, and the purpose of a needle bearing is to get a bearing into a tight space. That's really where they're most useful. There are also tapered roller bearings. If you've ever replaced bearings on the front end of a rear-wheel drive vehicle, you've probably encountered these. And so tapered rollers are kind of like cylindrical rollers. The difference is that they are, as the name implies, tapered. And so it's not just a plain cylinder. It tapers down on one side. And the reason for that, if you think about it, is as this thing rotates, the upper edge has to rotate around a longer distance, because this inner bearing is also tapered, and maybe you can see it on video. The outer raceway is also tapered. There's a taper like this on it. And so the distance that the outside diameter of the rolling element has to travel is farther than the distance the inside diameter of the rolling element has to travel. And so what that means is, since the angular speed of these has to be the same because it's just one body, what that means is that this side has to be smaller in size than the other side. Otherwise, one would be trying to get all the way around faster than the other, and you'd end up with sliding somewhere in the bearing. And sliding in bearings is a bad thing. As a matter of fact, a friend of mine that was an engineer had to told me once that you can't make the rolling elements and the raceways too smooth. If you do, what will happen is there will be sliding in the bearing as it operates, and rather than all of the elements sharing the load equally and being stressed and relieved, what will happen is it'll slide in just one area of the element will wear, and the bearing will fail prematurely. So you actually have to control the surface roughness but not make it too smooth, which was interesting. I had never thought of that. And in fact, bearings are one of those areas where you really have to go to the manufacturer and ask for an applications engineer just to make sure your design is going to work, or make sure you follow their design guidelines religiously, because it turns out bearings are very standardized, and you can switch out bearings from one manufacturer to another pretty easily because the sizes are all the same. That doesn't mean you're getting the same kind of bearing. Not only can the bearing innards, basically whether it's a ball bearing or a cylindrical type of roller, not only can that be different, but the quality and the materials and all of that make a big difference from manufacturer to manufacturer. So now if you stick with a name brand, you can pretty much switch out to anything, but you have to be very careful. And one of the temptations is to buy cheap Chinese bearings at this point in time. Chinese make some good bearings, they make some bad bearings. And so the temptation may be to just buy the lowest cost bearing, but there's no guarantee that that bearing is really any good. We'll talk more about that a little bit later. So these are good for, these tapered bearings are very good for heavy radial and thrust loads. And you can actually get double row bearings like this. I'll show you one in the context of a housed bearing here in a moment. There are also what are called spherical roller bearings. Now these are a little bit different. Hopefully you can see this okay. This is a spherical roller. The elements themselves, instead of being just plain cylinders, think of sort of a barrel shape, okay, like a wooden barrel, but not quite to that extent, okay. Now the interesting thing about these are a self-aligning, this is a self-aligning bearing, and let's see, I don't know if it mentions who made this one. Made in Canada. This is an SKF. Alright, so this is an SKF bearing. I couldn't remember, but anyway, the bearing elements themselves aren't just cylinders, they have some taper. And what they do is they mate with a outer race whose raceway is on the surface of a sphere. And that way, hopefully you can see this, you can have significant misalignment between the inner and outer race. Now you're not supposed to do it to the point where you've got elements not even contacting the outer raceway. Okay? That's not good. You don't want that. And by the way, it's kind of hard to get this thing back together once you do that, because the elements can actually pop out a little bit, and you got to find the one that's holding it out, push it in, and then a lot of times on the opposite side you have to push it in too. And there's a lot of interesting features here. I'm not sure if it'll pick it up on video, but the outer raceway here has a groove in it and holes, so that this is made to go in a housing and interface with some type of oil or lubrication system. But anyway, this is a nice bearing because it can take very heavy radial loads, moderate thrust loads because of the shape of the elements themselves, but it's very self-aligning, and so that's the main feature of this bearing. Now there's a friend of mine went up to the Studebaker Museum in South Bend and brought me back these pictures. I had to include them. This is a huge spherical roller bearing. It's like what I've got here, but there's no way I could pick it up because I think this thing is, yeah, over a ton, 2,960 pounds, almost a ton and a half. And this bearing was used, it said, and they took a picture of the plaque, that's where I got this, used in steel mills, paper mills, large ships, rudder shafts, and mining dragline cranes. So these were used in huge machinery, but it's actually a spherical roller bearing, which is interesting. And of course, you could imagine in large machinery, it's very difficult to build the machinery in the first place, let alone get it, aligned perfectly. And so a self-aligning bearing could be a big benefit. It was made by Torrington, and I think Timken and Torrington either merged or Timken bought them out. Donated by Timken Industrial Bearing as a sample. So anyway, just an interesting bit of Indiana history. There are also thrust bearings. Unfortunately, I don't have any examples of those, but thrust bearings are made to take complete thrust loads, and they can come in a ball shape for the element or more of a cylindrical or typically a tapered shape. And these are made for taking pure thrust loads. Typically, they're not really made for radial loads. And you can see that there's not really such a thing as an inner and outer race. It's really an upper and lower race in this case. You can see on the left how the ball is sandwiched between two races. And of course this would be revolved around a vertical axis this time. Both of these would, to complete the bearing. There are several different types of bearing housing. Sometimes the bearing housing is made right into the frame. If you think about a transmission, for example, for an automobile, it's very common for the bearing housing to be part of the frame of the transmission. But a lot of times also you mount a bearing to a frame that is a bit more crudely made. It's not really machined out. It's maybe welded or maybe it's bolted together. And so there are what are called pillow block bearings, and pillow blocks and many other types that are made for mounting to a frame, except what's called an insert bearing. The nice thing about this system is you can get the shape of the block or the bearing holder in many different shapes, so it can be convenient for your machine, but then you can get many different options within the insert itself. Now of course in smaller sizes only certain things are available. Here's an example of a pillow block that is actually made of plastic, and the insert you can see here, and typically there are holes in the outer raceway, which you can kind of see in the picture there, and the grease nipple goes through the housing to access the holes, or hole typically, and especially in a size like this, probably only one hole, in the outer raceway and the outer surface, so that you can get grease down into the bearing. Now one big problem with these things, and something you should know about, it's very common to introduce dirt into the bearing by greasing, because typically in a machine environment you're using them in a dirty, dusty, whatever environment, and that dust and dirt collects on the top of the fitting, and as soon as you put the mating grease gun onto it and squirt it in, all you've done is push dirt and grease into the bearing. So it's actually important that part of your maintenance schedule be to clean that fitting and then insert grease. But there's many different options with these things. I've got some like this really large pillow block bearing, and this one's been cut away so that you can see some of its elements. If you can't see it, I'll describe it. There are two taper roller bearings in this one, and they're back to back, so it can accept a significant thrust load because you've got thrust support in both directions from the taper roller bearing. Maybe you didn't notice it before, but although a taper roller bearing is made for accepting thrust loads, it can only accept thrust loads in one direction. If I push this inner race this way and the outer race in the other direction, great. But if I push them the other way, they separate easily. So thrust bearings only accept load in one direction. Now another interesting feature you can see from this is that the inserts, or the insert bearings, hopefully you can see this, typically are self-aligning. So if you look at the picture on the screen, you'll notice that the outer raceway has sort of a crown to it, and that is part of a surface of a sphere. Just like self-aligning bearings, that's made so that the bearing itself can move in the housing, and hopefully you can see that. There's a pin right in the center here that's going back and forth as I move this insert around. Now this particular one, you can take the insert out pretty easily because you can simply unbolt the upper portion of the housing, and of course there's some pins here to align it all when you put it back together, but you can replace this insert fairly easily. Now of course this one's been cut apart so you can see it. But this is a really good system, and it's fairly common because, you know, if you think about something in your life like a go-kart. Many of you probably had a go-kart. I just bought one for my daughter last summer or so, and she's enjoyed it. I think I'll have her drive that before she learns to drive a car, because she still hasn't figured that one out completely, but she's only 11. She's got time, you know. But if you think about building a go-kart, you weld together the frame, and then you want to attach, say, a solid shaft for the rear wheels, right? Well, that shaft is a live shaft. In other words, the shaft turns. It's not a dead shaft. Now, some go-karts do have dead shafts. It's just basically a stud that sticks out. You put the wheel on. The wheel has bearings, and it rotates around this dead shaft, and you have a chain that drives the sprocket. But in the case of her cart, it's a shaft that goes across and actually drives both rear wheels rather than just one, and that's the advantage. So if you're going to have a live shaft, that shaft has to rotate relative to the frame, but the frame, once it's welded, is not all that precise. It's not all that exact. So you need a bearing that can be self-aligning, and what's typically used on a go-kart, at least, are bearings more like this. Now, these two are tied together. I haven't taken them apart. A student was kind enough to donate these to me from his company. He doesn't own the company, but his company mentioned cheap Chinese bearings. Well, the attraction of them is that they're cheap, right? But how do you know that they're any good? Well, his particular company was testing these bearings, and so they basically wore them out on a machine to see exactly what they could do. You know, load versus life, and we'll talk about that in a minute. So anyway, this one you can really see it. You've got this fairly cheap pressed steel or sheet metal housing that the bearing insert rides in. You can see how that bearing insert pivots around so that you can clamp this to the frame or bolt it to the frame, but then the shaft in it has play, and you can align it, you know, across a frame that is, you know, welded and so not very precise. Of course, these are much cheaper than the more industrial pillow block type bearing that I showed you, and I thought I had another pillow block. I guess I don't. There's also flange bearings, and I'm not sure about the terminology of these. To me, they're all essentially the same thing. Here's a flange bearing. It's basically just an insert. Same idea. It can be rotated within the housing to some extent, and then you have the bolting the bolting axis in the same direction as the shaft axis. So this is easy to just slide on and then bolt up to a surface. So there's many different options in these. There's another type that I don't even have in the presentation. It's this type, which is interesting. You know, you bolt it on one side rather than on both sides of the bearing. But all these are essentially the same idea. You've got the insert, you've got a grease fitting for putting grease into the rolling elements, and you've got options in the insert as well, which is nice. Here's a flange cartridge bearing. I don't have one of these handy. I was kind of looking around. And I don't even have this one in the slides. There's another one where you mount it across the bearing. This one's been cut away so you can kind of see the regular just balls in it. So as I rotate this, you can see those balls, and you can see the seal that's been cut away. There's actually a seal here that's really not supposed to rotate. Maybe you can see that on video. It's got a piece of felt here, and it's supposed to seal the grease in this bearing to keep it from coming out, and of course to keep dirt from going in as well. But those are all what I would refer to as housed bearings, pillow blocks, other types of housing, and they're all typically insert bearings that can be rotated because their outer raceway is a sphere, essentially a portion of a sphere. Here's some pictures of some bearings in action. Now these, I can't take credit for these photos or for this machine design. Professor Dews did a lot of large-scale machine design. My experience is more in small-scale machine design. I've designed machines that are basically fit into a 1-inch box and perform a job, and had features on them that were on the order of, you know, a 1/2,000th of an inch or so. But anyway, Professor Dews is at the other extreme end, and part of his experience is in making shaker machines, basically machines that you put parts in and shake them around for various finishing purposes. And so these are very large machines. The springs there are probably, you know, 10 inches in diameter, 8 to 10 inches in diameter. So these bearings are actually very large. You can't really see it, but there's some offset weights, and the bearings have to support these weights as these weights are slung around on a shaft. That's what actually causes the shaking motion of the machine, or these offset weights spinning around. So the bearings take a beating on these things, and you can see these have been filled with grease, and either the grease has leaked. I don't think this machine failed because it doesn't look like it's actually been painted yet. Looks like just a sloppy job with the grease. I'm really not sure of the story behind it, but these are fairly large bearings that are being put into place on the machine to support the shafts. Here's a bearing on an amusement ride that I don't think I would get on as soon as I saw the bearing. This is a simple pillow block bearing. You can see that this thing has significant misalignment, and it's seen better days. It's time for it to be replaced. Some interesting features here, though, that we'll approach later when we talk about pulleys and sprockets and so forth. But you can see that this has been sort of just jerry-rigged, and like I said, I don't think I would ride this thing given the condition of that bearing. Here's another closer up view of some pillow block bearings, and one thing you might notice is that, of course, the frame these are riding on has been welded, and so it's not particularly precise, but the tensioning of the belt is done by what's called a jack screw. That little screw in the upper left sort of section, well, controls bearing 2's position, can be turned in order to tension the belt and move the entire pillow block along, and then the bolts can be, or screws probably in this case, can be tightened down to hold and clamp bearing number 2 in position. Now it looks like that there are 4 separate flanges that have been welded in place and threaded so that a jack screw can be inserted in the position of all these 4 bearings can be adjusted. Here's another view of a similar design. These are slightly larger bearings than the last one, but you can see the jack screws in place on the rear 2 bearings, but I think the jack screws on the front are hidden by the timing belt that you see there. And you can actually see the offset weights that sling around and cause the shaking to occur. Now the materials that bearings are made from, as I've stated, have to be very hard because they're subjected to very high contact stresses, and basically the fatigue life of the material is related more closely to the ultimate strength of the material. And so very hard materials have higher ultimate strengths. And in the case of a bearing, you don't have a lot of energy stored in deflecting the material, so it doesn't have to have extreme toughness or anything like that. But it does have to be high strength material. Now usually these are steels, or even ceramics are being used fairly commonly these days. Now, how do you size a bearing? Well, everything's based on what's called the load-life relationship, and it's not a linear relationship. In fact, the life is measured in revolutions. That's on the left-hand side. There's 2 lives, L2 and L1, and then there's 2 different loads, P1 and P2. And notice these are inversely related. The higher the load, the shorter the life. And then, as I said, it's not linear, and so in this case the model that fits the data is just simply an exponent on the ratio of the loads. We'll dive into this a little bit more here in a second. But that exponent K is either 3 for ball bearings, so round spherical elements, or it's 10/3 for rolling elements, things like taper rollers or spherical rollers, or just simple cylindrical rollers. So make sure you know how to change that. In our case, in our book, we will stick with ball bearings more than cylindrical rollers, so most of the time K is going to be 3 in this class. Now, if you lightly load a bearing, the bearing will last a long time. If you load it, with a very large radial load or a very large thrust load, you'll have a shorter life. That's just the way that these things go. There's a term that's used, though, you need to know about. It's very common. It's called the L10 life. It's the amount of life, or I should say cycles. That's usually how it's measured, is the number of revolutions of the bearing. It's the number of revolutions before 90% of the bearings that you have are still working and 10% have failed. So if we have 100 bearings, okay, and we run them all with the same load, and we measure how many cycles we get out of them, we won't stop and call a certain number of cycles the L10 life until 10% have failed. I hope that makes some sense. This is basically the standard for bearing lives. Everybody uses it. The L50 life would be where 50% survive and 50% fail. Now this also is kind of special. It's called the average life, and it's about 5 times the L10 life, but that's not exact, and it depends on the bearing. L50 is less common than L10, but it is something you need to know about. Now there are some recommended design lives for bearings and for machines in general. You may be a little bit upset to realize that your automobile is probably designed to only last 1,500 to 5,000 hours. In fact, maybe you're not concerned about that, but if you figure out how many hours there are in a year, you realize your car is not designed to last a year. You might say, oh, well, that makes perfect sense. No wonder cars fail so much. Actually, we're talking about operating life. So in reality, you don't operate your car 24/7. If you think about a cab, okay, you notice that cab cars seem to just be kind of worn out all the time. You ever notice that? The reason for it is that they're really not made to work as many hours a day as a cab driver works. So cars in general are not made to operate as long. In fact, there was a time, I don't remember what vehicle it was for. It was for a truck. It may have been the F-150 I have, but I think it was something else because it's been a while. But anyway, I went into an auto parts shop to ask about parts for this particular vehicle, and they said, well, is it a wrecker? And I thought, why does that make any difference? So I asked the question, and they said, well, if it's for a wrecker, then the part price is, I forgot if it was doubled or 10 times typically. And the reason for that is because you require a longer life component, because wreckers are made to operate, and they operate, they're driving somewhere, and the loads on them are much larger than typically their size is designed for. So the components for these things and for ambulances are typically designed for longer lives, and so they are more expensive components. So anyway, here's some recommended life in hours. Now be careful, the L10 life we were talking about before is a life in cycles. It's the number of revolutions, whereas this is a design life in hours. Alright, now if we desire a greater reliability than 10% have failed after the stated life of the bearing, then we have to use what's called a life adjustment factor, a reliability factor, C sub R. And there's a table in your book that includes these. So you can take the LTN life and multiply it by a factor to figure out, say, the L1 life, okay, when 99% of the bearings have lived and 1% have died, basically. Now, at this point you may have said, well, you kind of sidestepped an issue because you said that the load makes such a difference, but I don't see load anywhere. Well, load is part of it. Remember, in the equation we had life on one side, that was L, and we had load on the other side, which is P. Now, unfortunately, there's a couple different symbols used for the load. One of them is L, sometimes we'll use R. Right now we're going to talk about a load called C, and it's just what's called the basic dynamic capacity, or also the basic dynamic load. So it's either BDC or it's just C, depending on whose bearings you're looking at. Basically, this is the life that a bearing can handle with an L10 performance for 1,000,000 cycles. Okay, 10 to the 6 cycles. That's what the basic dynamic capacity. So we finally brought it full circle. We said that an L10 life is the number of cycles that a bearing can take, but where 90% live and 10% die, basically. Okay, 10% are worn out. But usually we set that at 1,000,000 cycles and then figure out how much load it takes to cause 10% of the bearings to fail after 1,000,000 cycles. So sort of the standard load, or the standard life for L10 life, is 1,000,000 cycles. Now look at pages 512 through 514. These are worth bookmarking because the data we're going to use all comes from your text, and it's all for simple single row ball bearings. Okay, that's the data we're going to use in any problems, homework, design, etc. Unless you want to use in your projects, you can use other bearing data, but you have to just reference it for me. But it has to be good data from a reputable manufacturer. But anyway, bookmark 512 through 514 because there's a lot of data there. In addition to the basic dynamic capacity, see, there's also what's called a basic static load, or basic static capacity, as well as size information and all sorts of things that are really good. I'll show you more about that in the context of the example problems, but for now just bookmark those pages because you're going to use them and need them. Now if we take the load life equation and we put in the standard L10 life of 1,000,000 cycles and then move it to the other side, then we just have times 10 to the 6 on the right hand side. Now if that is the standard number of cycles, the standard L10 life, then we'd have to put in the basic dynamic rating of the bearing for that load. That's why you see the letter C replacing one of the P's in our load life equation. So now finally we've got it into a more useful form where we can say, okay, given a bearing and I know the L10 life is 1,000,000 cycles, and I know, say I select a bearing and know that it has a basic dynamic load rating of, I don't know, let's say 2,000 pounds, okay? Then I can put in for C 2,000 pounds, and now I've got a load-life relationship, so I can put in some other load, say 500 pounds, and ask the question, how long would it last? What would the L sub D, the design life, be? Okay, so this life now is measured essentially in millions of cycles, see? So, but we got to be careful about this, because this design life is the expected L10 life. Now, be careful. The standard L10 life is 1,000,000 cycles, but now we're talking about how many cycles it will be before 10% of the bearings fail. Okay, at a different load. And now it's not 1,000,000; it's on the left-hand side. Okay. Hopefully, all that makes some sense. And again, this should clear up a little bit when I work some example problems for you. Now, what if a bearing has, what if it's a little different? What if it's loaded a little differently? Well, if there are only radial forces, and remember, radial forces are forces that act perpendicular to the shaft. They act in the radial direction of the bearing. Okay, so here's our bearing. We have a radial load on that bearing and no thrust load. Well, in that case, most of the time, the load that the bearing experiences, P, will simply be equal to R, the actual radial load, but we've included this multiplying factor V to take into account when the outer race rotates. Most of the time the inner race rotates. In other words, most of the time the outer race of a bearing is held by a housing and the inner race rotates with the shaft, because most of the time you have live shafts. But sometimes that's not the case. Sometimes you have a dead shaft and the inner race just holds onto the dead shaft while the outer race rotates. So make a note for yourself that V is just, V is equal to 1 for live shafts and V is equal to 1.2 for dead shafts. Or you can just make a note for yourself about when inner and outer races rotate. And these notes should be made on page 517 or so, because that's where we're talking about how loads can vary a little bit on bearings. Now, sometimes you'll have radial and thrust loads applied to a bearing. In that case, what we're going to do is basically calculate an equivalent radial load from it. Now, V is as it was before in this equation for P. P equals VXR plus YT. V is just as it was before, but now R is the radial load while T is the thrust load. And you'd want the units to be the same, both pounds or, say, newtons. But X and Y are factors that depend on the design of the bearing. Now, in our case, for our particular case and the problems you solve in this class, we're going to simplify things a little bit. X will always be equal to 0.56. And if you look at table 15.4, I think there's a little note underneath it. You need to grab your highlighter, highlight that note, or next to the equation in the book, which is on the left-hand side page, I think page 516, make a note to X and say always 0.56 for this class. Okay. There's a procedure much like this that's used in industry, where we're simplifying things just a little bit for the sake of the course. And if there's some other more complicated sizing equation that a manufacturer has, you should learn to use it. We're just trying to introduce you to the concepts needed to understand them. Also, typically in bearing application, if it's a critical application, you really need to get with an application engineer from the company where you intend to buy the bearing, and make sure that the bearing that you select is appropriate for the given application. Now, the Y factor depends a lot on the ratio of the thrust to radial load. There's a whole design procedure that you need to tab, so this is another page worth tabbing, and the details I'll go into in an example problem. Now, failure is something that does happen with bearings. Bearings do not last forever. They can last very long times, but they're not made to last forever. And Timken actually has a really nice failure chart, and they've also got a design guide for failure, really, that talks a lot about the different types of failure. I've included links to those on the course site in this learning module, so make sure you look through them. But generally it comes down to a couple of different causes. The number one cause being no lubrication or dirt in the lubrication, foreign material, that causes problems in the bearings. That's because the tolerances in bearings are usually about an order of magnitude higher than typical machining. Usually you've got tolerances on the order of 1/10,000th of an inch, or 0.401. No, I'm sorry, 301. So it's the 10,000ths place after the decimal place, which is that's where the tolerances for these bearings are typically that's where they begin. Another thing that can cause problems is overloading, and it could be possible that the bearing is improperly sized, or you could have bought a cheap bearing and replaced a quality bearing with something that's cheap. There could be misapplication. Bearings are not appropriate for every single application. Electrical discharge. There are many different types of discharges, and even one I didn't include some vibration things that can cause problems in bearings. So make sure you look through these. It's a good sort of help you solve the mystery of what happened when the bearing failed. And of course, applications engineers can help with this as well.